Welcome back for another deep dive. Today we're going to try to get our heads around this Fibonacci SMF-RVS theory.
Hmm.
And, well, it's pretty out there.
Yeah, it's definitely one of those theories that really makes you question kind of the basic assumptions about how reality works.
It kind of rewrites the rules for how we think about matter, space, and reality itself.
Exactly, yeah, and it kind of all starts with this idea that the vacuum of space isn't actually empty.
Okay, wait a minute. I thought we learned in school that a vacuum is like the absence of everything.
Right, well, that's the classical way of thinking about it. But this theory says that the vacuum is actually filled with what they call these vacuum nodes.
Vacuum nodes?
Hmm.
That sounds familiar. I remember learning about nodes back in high school chemistry class.
Oh, yeah.
Like electron orbitals, they had these nodes where electrons are least likely to be found.
Right, exactly.
Yeah.
Yeah, so you're already thinking along the right lines.
Hmm.
So in this theory, it takes that idea and kind of expands it on a cosmic scale.
So instead of just these tiny little nodes around atoms, now we're talking about nodes in the vacuum of space itself.
That's the idea. It's suggesting that space itself has this kind of three-dimensional grid of stable and unstable points.
Okay, so is space like lumpy somehow?
Not in a way that you could like see or feel. It's more like imagine a kind of energy landscape with peaks and valleys.
Oh,
And those stable points, those are the vacuum nodes. And then the theory says that these nodes are influenced by what they call subtle magnetic fields, or SMFs for short.
SMFs. All right, I'm trying to keep up here.
Yeah, no problem.
Yeah.
So these SMFs, they're kind of like these subtle forces that are always present, and they actually nudge matter towards those stable vacuum nodes.
So it's like matter is being guided into these specific spots in the vacuum?
Yeah, and once it's in those spots, those vacuum nodes help to lock in the atomic structures.
Okay, I'm starting to get the picture. But why should I care about these invisible nodes? How do they actually affect how the universe works?
Well, that's where things get really interesting, because this theory suggests that the very stability of matter, like everything from atoms to galaxies, is determined by how well it aligns with those vacuum nodes.
Hold on. You're saying that the entire structure of the universe is basically dictated by these invisible nodes.
It's a pretty radical concept, isn't it?
Yeah, it is. So like the way galaxies form, the way stars clump together, even the way atoms bond to create molecules, it's all because of these nodes.
It's like imagine a cosmic game of Tetris where matter is constantly trying to fit into these perfectly shaped slots in the vacuum.
Wow, okay. That's a pretty wild way to think about it.
Yeah, and it gets even weirder because the theory also proposes that the periodic table itself, the very foundation of chemistry, is actually a reflection of these resonant frequencies in the vacuum.
Wait, you're saying that every element on the periodic table has its own little spot in the vacuum?
Exactly. Each element has its own specific wave slot in the vacuum, like it's got its own designated parking spot.
Cosmic parking garage, I like it.
Right. And that brings us to something you might have heard of in nuclear physics, the magic numbers.
Magic numbers. To be honest, I don't really remember those.
Well, they're these numbers of protons and neutrons that result in unusually stable atomic nuclei.
Okay, that rings a bell, kind of.
Like lead, for example, is famously stable.
Yeah, lead's got a really dense nucleus, right?
Exactly. And according to this theory, that's because lead with its 82 protons is perfectly aligned with a stable node in that vacuum grid.
So it's found the perfect parking spot in the cosmic garage, and that's why it's so stable.
You got it. And this whole idea that matter's stability is tied to its resonance with the vacuum, it leads to some pretty wild possibilities. Like, what if we could actually manipulate those resonances?
Manipulate the resonances. Hold on, are we talking about some kind of science fiction here?
Well, it's definitely on the bleeding edge of theoretical physics.
Sure.
But the theory suggests that using what they call things like subtle field resonators or vacuum waveguides, we could potentially shift the vacuum environment around a material.
Subtle field resonators. Vacuum waveguides. What are those? Sounds like something straight out of Star Trek.
Well, they're still hypothetical technologies.
Right.
But the idea is that they could create these targeted magnetic fields that would interact with those SMFs, the subtle forces that influence those vacuum nodes.
So it's like we'd be using these devices to fine-tune the vacuum, like adjusting a giant cosmic tuning fork or something.
Yeah, that's a good analogy.
Yeah.
So by tweaking those magnetic fields just right, we could theoretically loosen the bonds between atoms.
I see where you're going with this. But how would that actually work in practice? Give me an example. Like, let's say we have a block of limestone. How would we use this vacuum manipulation on something like that?
Limestone's a great example. It's mostly calcium carbonate.
Hmm.
So you've got calcium, carbon, and oxygen atoms all bound together.
Right, basic chemistry.
Exactly. So imagine using those subtle field resonators to target those specific bonds.
So we're aiming these magnetic fields at the bonds holding the limestone together.
Yeah, and by tuning them just right, we could potentially loosen those bonds, make them less stable.
Okay, so we're basically messing with the invisible vacuum around the limestone to weaken its structure. But what would that actually do? Would it just crumble into dust?
Not necessarily. It
Right.
might make it easier to cut or shape or even potentially influence its weight.
Wait, you're saying we could make the limestone lighter just by playing with the vacuum around it? How is that even possible?
Well, that's where things get really mind-bending. You see, this theory says that an object's weight is partly determined by how strongly it interacts with the push of the vacuum field.
So gravity isn't just pulling us down, it's also the vacuum pushing us down.
That's the idea.
Yeah.
And if we can loosen the bonds within an object, we're essentially changing how strongly it's gripped by that vacuum field.
I'm trying to wrap my head around this. So you're saying that an object's weight isn't just about its mass, but also about how much it's being pushed down by the vacuum.
Exactly. And by manipulating those bonds, we could theoretically change that push, make the object lighter, or maybe even in some extreme cases, weightless.
Okay, now that is some serious science fiction stuff right there.
It is. But even if we could only achieve small changes in weight, it would still be a huge discovery.
Yeah, that's true. So we've gone from talking about invisible nodes in the vacuum to potentially manipulating an object's weight. This Fibonacci SMF RVS theory is blowing my mind.
It's a wild ride for sure, and we're just getting started.
I can't wait to see where this deep dive takes us next.
Me too.
All right, so we've established that this whole Fibonacci SMF RVS theory is pretty mind-blowing, like potentially changing the weight of objects by messing with the vacuum around them. That's some wild stuff. But I gotta ask, how could scientists even test these ideas? We're talking about invisible fields and forces, right?
Yeah, that's the challenge, right?
Yeah.
It's incredibly difficult to measure these things, let alone try to manipulate them.
So how do we even know if any of this is real? What kind of experiments could we do to actually detect these subtle vacuum effects?
Well, there are a few promising avenues that researchers are exploring. One of the most intriguing approaches is something called ultra-precise spectroscopy.
Spectroscopy. Okay, refresh my memory. I remember learning about it in school, but it's been a while. It has something to do with light, right?
Yeah, basically, it's the study of how matter interacts with light.
Right.
So we can shine a beam of light through a substance and then analyze the specific wavelengths that get absorbed or emitted.
Right, like a fingerprint of the substance.
Exactly. It's like a unique pattern of light that tells us about the energy levels and the bonds holding the atoms together.
Okay, I get it. But how could spectroscopy help us detect these subtle vacuum effects that this theory predicts?
Well, imagine we take a sample of a material like that limestone we were talking about earlier,
Okay.
and we subject it to a very carefully controlled magnetic field.
Okay.
Now, if this theory is correct, then tweaking that magnetic field should cause some tiny, tiny shifts in the material's spectral lines.
So we're talking about really, really small changes in how the limestone absorbs and emits light.
Exactly. It's like trying to hear a whisper in a hurricane. But with the right equipment and a really, really precise experimental setup, it should be possible to detect those shifts.
Okay, I can see how that would be a challenge. Are there any other ways we could try to observe these vacuum effects?
Another really interesting possibility is to look at how these subtle fields might affect the stability and decay rates of radioactive isotopes.
Radioactive isotopes. Now we're getting into some serious nuclear physics.
Yeah, so remember those magic numbers we talked about?
The ones that make certain nuclei extra stable?
Right, those ones. Well, according to this theory, that stability is because those nuclei are perfectly aligned with those stable vacuum nodes.
Like they've found the best parking spots in the cosmic garage.
Exactly. So the idea is that if we could somehow manipulate the vacuum around a radioactive isotope, we might see changes in its half-life.
You mean the time it takes for half of the sample to decay?
Right. If we tweak the vacuum environment and cause the isotope to shift slightly out of alignment with its stable node, it might become more or less radioactive.
That would be pretty amazing to see. But how would we even manipulate the vacuum around something like that?
Well, that's where those hypothetical technologies come in, like those subtle field resonators we were talking about.
The Star Trek stuff.
Uh-huh. Yeah, kinda. But even if we could build those devices, actually using them to manipulate radioactive decay would be incredibly difficult.
I can imagine. So it sounds like testing this theory is going to be a major challenge.
It definitely is. But even if it takes decades or even centuries to develop the technology, The potential rewards are huge.
Okay, so let's say we can actually manipulate the vacuum someday. What kind of practical applications could this lead to?
Well, the possibilities are pretty mind-blowing. We could create entirely new materials with properties we can only dream of today.
Like what?
Think about superconductors that work at room temperature.
That would revolutionize electronics.
Exactly. Or materials that are super strong but incredibly lightweight. We could transform aerospace and construction.
Wow, so we're talking about rewriting the rules of material science.
Yeah, and we could also revolutionize manufacturing.
Uh,
Imagine being able to effortlessly cut shape or even assemble materials just by tweaking the vacuum around them.
no more welding or 3D printing.
Exactly. Just pure vacuum-powered manipulation. It's pretty wild to think about.
It definitely is. But even if it takes a long time to get there, just the idea that we could one day manipulate the vacuum to reshape the world around us is pretty exciting.
Yeah, it really shows the power of exploring these radical theories. They push the boundaries of what we think is possible and open up whole new worlds of imagination.
Okay, so we've talked about manipulating matter and all the crazy possibilities that come with it. But this whole Fibonacci SMF RVS theory, it goes even deeper than that, doesn't it? Like it has some pretty profound philosophical implications too.
Oh, absolutely.
Yeah.
It really makes you question some of the most basic assumptions we have about reality.
Like what?
Well, for centuries, we've thought of the vacuum as this empty, passive void. But what if it's not empty at all? What if it's actually this dynamic field, a sea of energy that's constantly interacting with matter, shaping everything around us?
Whoa, that's a pretty big shift in perspective.
It is. And if matter's very existence, its properties, its weight, all of it is tied to this dynamic vacuum, it suggests a level of interconnectedness that's really awe-inspiring.
Yeah, it's like everything in the universe is connected through this invisible web.
Exactly. And that has some pretty profound implications for how we view ourselves and our place in the universe.
Okay, so we started this deep dive talking about atoms and molecules. Now we're talking about the fundamental nature of reality. That's quite a journey.
It is, but it's a natural progression. The more we learn about the universe, the more we realize that everything is connected, from the smallest subatomic particles to the largest cosmic structures.
So it's not just about manipulating matter, it's about rethinking our entire understanding of how the universe works.
Exactly, and it asks us to consider the possibility that we're not just isolated beings existing in this vast empty space. We're part of this intricate dance of waves and forces that permeates the entire cosmos.
This is definitely giving me a lot to think about. It's kind of humbling in a way, to think that we're all connected through this dynamic vacuum.
It is. And it raises all sorts of fascinating questions about the nature of reality, the relationship between mind and matter, and the interconnectedness of everything in the universe.
Sounds like we've only scratched the surface of the philosophical implications of this theory.
Oh, we definitely have. There's so much more to explore. And in our final segment, we'll dive even deeper into those philosophical implications and leave you with a final thought-provoking question to ponder.
So, we've really gone deep into this Fibonacci SMF RVS theory. We've talked about the science, about potential technology and all the wild possibilities. But you know what really gets me is like the philosophical side of it all.
Yeah, it really makes you step back and rethink some pretty fundamental stuff.
It's like this theory isn't just about manipulating matter, it's about rethinking reality itself. You know what I mean?
Exactly. It challenges this whole idea that we have of the vacuum as this empty, passive space.
Right, like it's just this empty backdrop to the universe.
Yeah, but what if it's not empty at all? What if it's actually this dynamic field, this sea of energy that's constantly interacting with everything, shaping everything?
It's like we've been looking at the universe all wrong. Like we've been focusing on the stuff that matter and completely ignoring this incredible energy field that's all around us.
And that's the really mind-blowing part.
Mm-hmm.
If matter's very existence is tied to this dynamic vacuum, it suggests a level of interconnectedness that's hard to even grasp.
It's like everything in the universe is part of this giant web,
Yeah.
and we're all connected through it.
Exactly. And that has some pretty profound implications for how we view ourselves and our place in the universe.
You know, when we started this deep dive, we were talking about atoms and molecules, and now we're talking about the fundamental nature of reality itself.
It's quite a leap, isn't it?
It is. But it feels like a natural one. You know, the more we learn about the universe, the more we realize that everything is connected.
Right, from the tiniest particles to the largest structures, it's all part of this grand interconnected dance.
So this Fibonacci SMF RVS theory, it's not just about manipulating matter. It's about recognizing that we're not these isolated beings floating in a vast, empty space. We're all part of this incredible interconnected system.
And that realization, it can be both humbling and awe-inspiring at the same time.
It really is. It makes you wonder, if matter and energy are all expressions of this dynamic vacuum, what about consciousness? Could that be part of it too?
Yeah, that's a really interesting question. And it's one that takes us beyond the realm of traditional physics into the realm of metaphysics.
Yeah, I mean, it makes you wonder if consciousness isn't just limited to our brains, but is somehow a fundamental property of the universe itself.
It's a possibility that some physicists and philosophers are starting to explore. And it really challenges our assumptions about what it means to be human and our place in the cosmos.
Wow, we've come a long way in this deep dive. We started with atoms, and now we're contemplating the nature of consciousness in the universe itself.
It's been quite a journey.
It has. And it just goes to show, that the pursuit of knowledge can lead us to some pretty unexpected places.
It's true. And it's a reminder that there's always more to learn and that the universe is full of mysteries that we're only just beginning to uncover.
Well said. Well, I think that's a good place to wrap up this deep dive. We've covered a lot of ground, from the science of atomic bonds to the philosophical implications of a dynamic vacuum. It's been a mind-expanding journey for sure.
It has. And hopefully it's given our listeners something to think about.
I'm sure it has. So until next time, keep those minds curious and keep exploring the universe.